All right, well, welcome back from the break, everyone. It is now my pleasure to introduce Carnegie Mellon's Provost and Chief Academic Officer, Jim Garrett. Jim is a nationally recognized engineer and a lifelong Tartan. He bleeds plaid. Provost Garrett has been a steadfast supporter of the Scott Institute for Energy Innovation for years. Jim, thank you so much for your support, and please join me in welcoming Provost Garrett.
Thank you, Daniel. I really do appreciate your leadership as executive director. Where'd Daniel go? Oh, he's trying to wrestle everybody, and I'll stretch for a little bit so that we can get the audience back in the room for our speaker. It is my true pleasure to join you all today, you know, to me, I think I've seen some of our CMU leaders here, and more will join us in a moment. And I do appreciate all that they've done to make the Energy Week possible. It's events like this that truly showcase the power of our community here at Carnegie Mellon. I also want to thank the scholars and the industry partners and the policymakers that are in the room. Thank you for being here. If you weren't here, these discussions wouldn't nearly be as meaningful. Your presence really helps make Energy Week the success that it is. This year's theme is reinventing the grid for our electrified future, and acknowledges that the resilience of our infrastructure relies on constant innovation. And our aging grid faces unprecedented pressure across all sectors. I mean, we've experienced a number of situations just within the past several months that have really put a lot of pressure on the grid. At Carnegie Mellon, we address these challenges through a holistic, interdisciplinary approach that bridges engineering, computer science, and public policy. As a civil and environmental engineer myself, I have a deep personal commitment to the built environment. I believe that the future of energy does not and should not rely on, I'm going to use this term carefully, quote unquote, on dumb cables and poles. I don't mean, you know, to be disrespectful. They just have no sensing in them and no, prescience of what is happening. And instead, I envision that our smart infrastructure, again, with quotes around it, it should be adaptive, should be using lots of sensing to harness what's happening in real time and anticipate changes that are needed and failures that are emerging, and really help take every dollar that we spend and have it be spent as efficiently as possible on the maintenance of these facilities. At CMU, the real-world impact of our research is made possible through strong collaborations with industry partners. And that's why I'm delighted to introduce a leader who truly understands the power of these partnerships. Deborah Gracio, or Deb, as I was introduced to her, is the laboratory director of the Pacific Northwest National Laboratory. She leads an extraordinary team of over 6,000 staff with an R&D budget of $1.6 billion. And under her vision, PNNL is advancing innovations that address our most pressing challenges in science, engineering, and national security. Deb is an internationally recognized leader and fellow of the American Association for the Advancement of Science. And as CMU's collaboration with PNNL continues to grow, we value the vital work that's being done between our two organizations. So we're fortunate, very fortunate, to have Deb here to discuss grid modernization, reliability, and resilience. So please join me in welcoming Deb Gracio to the stage. Oh, there you are.
Thank you.
Thank you. Thank you for being here.
Thank you very much. Am I on? Yep, there we go. Okay. Here we go. Well, thanks everybody for joining us today and for inviting me here to be with you. I'm very excited. I will just share a couple of tidbits about myself before I get into this. I've been at Pacific Northwest National Laboratory for 37 years. I grew up there, if you can really say that. I came right after grad school. I actually spent time there as a graduate student and started my career in climate physics, moved into computational chemistry, computational biology, and national security at the end before I became the lab director. And the reason I tell you that is you've already heard a little bit about the national lab system from one of my colleagues from NETL, but I want you to understand how impactful the labs are because we have such a diversity of work that we do. And so I'm going to spend some time today talking to you about our work in the grid. So let's get going here. So Pacific Northwest National Laboratory was born out of the Manhattan Project. After the Manhattan Project, where we created the plutonium necessary for the weapons that were being created, the cleanup mission became very important to our area. Hanford is one of the worst waste sites, if you will, because plutonium was produced there, but they use 3 different methods. So there's a lot of different kinds of waste in that facility, which has really brought the laboratory to bear on the kinds of problems there. We were part of the Atomic Energy Commission's advancement of trying to figure out how to clean up the waste. We became the research arm of Hanford at that point in time. Today, about maybe 6% of our work is in the support of Hanford, but that's really where our roots started and where we came from. I won't spend much time on this slide because I think you've already heard a little bit about the National Lab System. There's 17 national laboratories. We are one of them. We are one of the Office of Science laboratories, which may sound silly when I tell you that 50% of our work is actually in national security. But what I love about that is we're based in the roots of basic science. And basic science really feeds a lot of the mission of what we do at Pacific Northwest National Lab. The other thing that's important here is that this network of R&D work that's done by the Office of Science Labs brings basic sciences to everything we do in terms of scientific discovery, energy, national security, and the environment. So everything we are doing is really rooted in that space there. Today, as I think you already heard, we have about 6,000 staff, an annual budget of about $1.7 billion in research and innovation funding annually. Our main campus is in Richland, Washington, which is what this picture is showing here. It's on the desert side of the state of Washington. We also have a facility in Seattle, Washington, one in Portland, Oregon, and we have a facility off the Strait of Juan de Fuca off of Washington State's Olympic Peninsula. It's where we steward the only marine sciences research laboratory for the Department of Energy. We also have quite a few staff based in Washington, D.C., where they're embedded in with our sponsors. So as a really diversified national lab, as I just shared with you based on my own career, we really contribute to a vast majority of missions. We draw on signature strengths in chemistry, biology, data sciences, computing at large to really serve that mission that I talked about earlier, scientific discovery, energy resiliency, and enhancing national security. Our expertise is really focused in contributing significantly to advancing our nation's energy goals and including modernization of the electric grid, which is really what I'm going to spend time talking to you about today. So grid modernization, it's a critical element of how we sustain and how we continue to grow the capabilities. So I like to say, within DOE, they say frequently, AI for energy and energy for AI. And that's an important thing to remember, is we won't be able to do many of the advancements that we talk about today without a stable, reliable, and secure grid. And so our focus has been in modernizing the grid as part of a joint effort with multiple laboratories, but the National Lab of the Rockies was critical with PNNL in starting the Grid Modernization Laboratory Consortium in 2014. The goal here was to foster collaborations amongst national labs and industry to develop advanced technologies that were going to focus on clean energy, on integration of technologies, on grid security, and improved performance and operations. It brought together staff with expertise and experience in diverse areas from across the lab and across all of the labs and industry to work on solutions that could tackle complex national problems. Our grid work combined expertise in power electronics, in computing and data analytics, in cybersecurity, chemistry, and material science to enable the grid of the future. And when we think about all of these things, we really want to realize a grid modernization that realizes outcomes such as affordability, reliability, and security. Much of what you've heard this whole week probably, but at least this morning and this afternoon, has really been focused on those efforts. Apologize, this light's bright, so I'm going to take off my glasses here. Our goal with the grid modernization activity is to protect the nation's power delivery system from cyber threats, from physical attacks, and from natural events, weather events, natural disturbances that might happen, whether it's a hurricane, a wildfire, et cetera. We address load volatility. You heard a little bit from Lou, I believe, about large electric loads and the problems that data centers and bit mining services are causing on the electric grid, and I'll talk a little bit about this in a while. These objectives really cannot be addressed in silos. We have to think about how they all play together in a system, and that integration is really, really critical to the way we think about supporting the grid. At PNNL, our grid work is focused in 3 core areas: modeling and analytics, energy storage, and all-hazard energy resiliency. Underpinning all of this and enabling what we do is AI. It's a really growing capability for us, but I'll also add autonomy and autonomous laboratories becomes a component of that. So I'm going to share some examples of this innovation that we're working on. Grid modeling and analytics really enables us to observe, understand, simulate, model, and predict grid behaviors. National labs have unique capabilities and facilities to conduct modeling and analytics. We have some of the most world-class computing capabilities where we can leverage the models on these systems. But we focus at the regional scale, while utilities are really focused at individual service territories. And it's thinking about that at the regional scale where it becomes the most impactful, because you can see what the interactions between systems are doing. Reliability and resilience and improving the stability of the grid is very important here. And more than a decade ago, we led a regional consortium to instrument the grid with sensors that provide real-time information on the state of the grid. Data feeds are sophisticated models of the grid, and tools were developed to analyze its performance. Again, allowing us to observe and understand and predict grid behavior. An example of this is the Dynamic Contingency Analysis Toolkit, which was developed jointly with ERCOT, which is the Texas's independent systems operator. And it helped power system planners assess the impact of cascading events and potential blackouts and suggest mitigations that would reduce the risk of these outages and create mechanisms and mitigations for technically sound ways of focusing that. We adapted machine learning models to identify the troubling patterns in the data and call those patterns to the attention of the grid operators. For large electric loads, which we talked a little bit about already today, we coordinated the first rigorous technical showing of how coordinated responses from large electric loads, such as cryptocurrency mining and data centers based on artificial intelligence, what that would happen to destabilize the US power grid. This was joint work with the Idaho National Laboratory, the National Lab of the Rockies and Idaho National Laboratories. These power demands really shift the way the frequency of the systems operate. And this is where I think some of the battery capabilities will really have an impact in being able to address that frequency shift. It's an amazing, if you could only see, I don't have the video here of the data, but it's pretty incredible when you see an AI run on a data center and when it stops, and the frequency load shifts is just tremendous. These power demands really from facilities can shift in the milliseconds without human input at all and rapidly reshape the way the grid is being designed and operated. That's an important component of creating this reliability. Our researchers modeled the introduction of more than 10 gigawatts of large electric load onto the grid and identified scenarios that could lead to these cascading failures and regional power outages. By grounding that conversation in data, decision makers can really use that information to assess the vulnerabilities and develop real-time mitigation strategies. So the North American Energy Resilience Model is a first-of-its-kind grid resiliency model that supports electricity reliability by modeling numerous U.S. energy sources. It layers that information and combines multiple independent energy and infrastructure models with systems data and realistic threat scenarios. For energy system planners, operators, government stakeholders, they really can focus on a broad base of these different potential threats to the system, look at the interdependencies, the consequences of their responses, and reduce risks from extreme events at the national scale. This leverages capabilities and knowledge from subject matter experts from across 8 national laboratories and partners at federal agencies and the power marketing administrations and the private sector. The delivery of NARM is at a national scale and provides energy modeling capabilities to all. This model has been used in a lot of situations, specifically in disaster recovery efforts. So an example of really incorporating AI into the grid is called PNNL's Chat Grid. It's a generative AI tool that allows system operators to ask specific questions and distills and brings all of that information together in a visual display, in a visualization that answers the questions and informs the decision makers. Users can ask a variety of questions about generation, capacity, voltage, power flow, and a lot of other things. And it all comes together in a visualization that provides the decision maker the various information layers in a way that they can approach it, right? So with a visualization, you're not reading long documents. You're actually just seeing in real time what's happening on the system. So grid scale energy storage is really important, and this is the next section that we wanted to talk about. Energy storage at the grid scale is vital to integrating various sources of energy. When you bring renewables in, you can create a lot of instability, but having that storage as a mechanism of balancing out what's happening on the system. Another example is peak shaving. So as you're running these data centers, and let's say it's hot outside, your air conditioners are running really hard, you're going to get some peaks that your systems may not be able to support. But when you have grid energy storage at this large scale, you can create more flexibility, you can create more reliability and more resilience of your systems. Battery technologies are an important part of this. So PNNL is a leader in battery energy storage, including flow batteries at grid scale level. I want to give you an example of some of the work that we are doing with Microsoft, where we were really accelerating the scientific discovery of new battery materials. So we worked on a computational challenge with them where they narrowed down more than 32 million potential electrolytes that could be used to create new materials, down to 150 promising candidates. But with the input of a researcher, this is one of the things I really want to highlight. A lot of people believe that when AI comes in, the scientists won't be necessary. But we would have never been able to solve this problem without the researchers that really understood chemical synthesis and what battery properties were necessary. They took the 150 promising candidates and narrowed it down to 18 potential candidates that were worth further exploration. And then they went through the process of synthesizing the material, the electrolyte, into a battery and testing the battery to really understand if it was a functional battery and whether it was going to work. Now that part took weeks because we didn't have an autonomous laboratory up yet. So the synthesis process took quite some time. All of that then ended up with a battery that we could test and understand and define whether those materials were of value. Now, I will highlight that the material that we found here was not something unknown to the community, but it did give us a chance to see how these tools could help us start to identify new materials. We're also using grid-scale energy storage on our own campus. So with an investment of $10 million by the Department of Energy, we're installing a 24-hour flow battery on our campus. And we're using it not only for our research, but also for peak shaving for our own lab. So we have a shortage of transmission capabilities in the Pacific Northwest. And so we don't have enough energy coming into our facility to be able to power all of the various instruments and systems that we need over the long term. And so we're using this battery as a way of helping us with the peak shaving during the summer especially, and when we need to run very large experiments. So we're eating our own dog food, if you will. We're not only doing the research, but we're utilizing it ourselves also. So we steward the Grid Storage Launchpad. This is a facility that was built a few years ago. We commissioned it about 3 years ago now, I believe. And it was built out by the Department of Energy Office of Electricity. And it was built to speed the development, scaling, validation, and implementation of next-generation long-duration battery techniques. It was designed and built with collaboration in mind. So our goal is that industry, academia will work with us to accelerate solutions to market. It's a first-of-its-kind facility in the nation, and it allows us to test and validate technologies at grid scale in partnership with industry. First battery from Invinity arrived in October, and when the Secretary of Energy was at PNNL in December visiting us, he pushed the little red button that said, "Start testing this battery." It really was that simple. But what this is really targeted on doing is fostering leadership in the U.S. in manufacturing the next generation of batteries that will help us ensure the reliability and resiliency of the grid. And so the final section I want to talk about is all hazard resiliency. It's really about bringing innovation and expertise to improve resiliency against natural and man-made hazards. So we have a broad set of modeling and analytics capabilities that characterize and assess how critical infrastructure is impacted by natural disasters. So you're seeing here an example of a simulation where we use these technologies during Hurricane Harvey. We've used them in a variety of other hurricanes as well as wildfires. So this is a tool suite that was funded by the Department of Homeland Security on National Infrastructure Simulation and Analysis Center that's based across a couple of national laboratories, including PNNL. And it's based there to understand the impact that storms will have or potential flooding impacts will have on critical infrastructures such as grids and the roads. So another thing that we've used this for is to look at the impacts of different locations. Let's say for the military location, what would the impact of a 100-year storm have on that facility? Maybe they don't have the roads they need to be able to get the people there. Maybe they lose communications. They'll lose electricity. If all of those things happen in a 100-year storm, how are they going to mitigate the consequences of that kind of an outcome? And so this suite of tools really helps them understand those consequences. Leveraging AI to aid in emergency response and recovery from all hazards is another really key important aspect here. So we've built the Rapid Analytics for Disaster Response System. So think wildfires, floods, earthquakes. We're using SAR radar. So the SAR radar, what's nice about that is it can actually see through smoke. So you can see what's going on underneath the smoke cloud there. It provides emergency responders with the ability to quickly assess the impact and the risk to infrastructure and give them the ability to make more informed decisions. Where do we draw the fire lines? How do we evacuate people from this fire? During the Maui fires, this technology was used by the Coast Guard to understand how to evacuate people and where they could go to help with that evacuation. It's been used in hundreds of events to assist first responders, emergency support functions, energy providers, and state and local governments. Another use that we had for it was in Ukraine. So during the Ukraine war, the power lines were getting shot down quite significantly. And one of the impactful things there was utility workers didn't have the ability to walk the line to know where the power lines were down. They were able to use this technology to understand where the power line was down and be able to go to that place and fix the facilities. They also used this to analyze flooding after the Ukraine Kakhovka Dam was breached and aided the response and recovery efforts during all of that activity. So this is being used now by the Bureau of Land Management for wildfires, by the Department of Defense, and by Homeland Security. So there's a lot of uses of this technology. So we had a great panel up here earlier about cyber threats. National security is really an important aspect of securing our grid. PNNL runs a program called CRIS, the Cyber Risk Information Sharing Program. It's a program that is a representative of public-private partnership. We have over 80% of the U.S. consumers served by utilities part of this program, where we gain insights to what's going on their networks. Using threat indicators that we have at a classified level, we can actually provide information back to the utilities of where the threats are on their system and what they need to do to protect their critical infrastructure. And so it's that partnership that's really critical here to monitoring and sharing the cybersecurity awareness across the vast stakeholders. Not only that, when you see what's happening on one network, what we don't realize because utilities only focused on their own network is what might be happening across the entire grid. And by seeing it on one network, we start to look for that threat across all of the grids, as well as the entire Department of Energy. And so it's really interesting to see how our adversaries are working on these systems. Our Electricity Information Operations Center is where we bring all of this together. The data, the tools, the models, the simulations. It's in a real-world control environment. And we use it to test advanced solutions in close partnership with industry. The EIOC, or the Electricity Infrastructure Operations Center, really consists of rooms that mirror what a real-world grid operations center would look like. The facility can be used for vendors, national labs, other government agencies and universities interested in grid-related research and development to come in, to use it as an education and training tool. We established the center about 20 years ago. Now we're building on that model to develop a state-of-the-art, AI-driven national scale enhanced visibility and event response capability. So many of these tools we've talked about, how are we building all of these together with an AI system wrapping it to really respond to the reliability of the bulk electric system and the security of our nation's critical infrastructure. So using AI-informed adaptive grid controls and protection schemes that really detect anomalies and enable response, such as autonomous reconfiguration and controlled islanding from across the bulk energy system. And then finally, scaling the grid. The Genesis mission, if you've heard anything about this, this is a brand new initiative within the Department of Energy, and it's an all-of-agency activity to accelerate science through artificial intelligence. So every component of the Department of Energy is engaged in the Genesis mission, but I'll also add that many of our sponsors, whether it's in the Department of War, the NSF, they're all coming to build out a relationship with DOE right now, and DOE is taking the lead in building an integrated platform that's going to connect the world's best supercomputers, experimental facilities, AI systems, and unique data sets to be able to provide scientific domain experts the opportunity to explore their data, interact with their data, and use AI to double the productivity and impact of their research and build out an innovation system like none we've seen before. It includes 26 lighthouse problems, if you will. They're national, think of those as national challenges. And there's one specifically focused on the grid to power, it's called Scaling the Grid to Power the American Economy. So using deep reinforcement learning techniques on newly integrated big data sources, the goal here is to reduce uncertainty, to improve insights, and to speed processes in grid planning, interconnection, operations, and security. This effort is really aimed at enabling 20 to 100 times faster decision-making and at least 10% improvement in electricity costs and reliability. I have to tell you, for me, as I said I was an electrical engineer, but I've spent the majority of my career doing computational sciences. I can't imagine a better time to be a lab director than what's going on right now with the Genesis mission. It's exciting for me because I think that the national labs, industry, and academia are coming together to work in ways that we've never worked before, to break down the silos of our activities and build out these kinds of skills across the country is really going to be impactful for us. So one of the things I want to end on here is the importance of building out our STEM workforce. PNNL is really, really excited about working with universities, high schools, grade schools. I think it's important that we bring everybody in to grow and upskill on these new capabilities. Internships are important to us. We have over 1,600 interns a year, and they could be anywhere from a summer to 8-10 weeks to a whole year. They could be a semester. We bring these interns in because they are our next generation of workforce. We also have joint appointments where we have relationships with, our staff have relationships with universities, and they're on joint appointment between the university and the lab, and vice versa. Members of the lab faculty have appointments with the laboratory, and they can work in both spaces. Right now, we have joint appointments for over 200 researchers at 60 universities. I want to point out my colleague over here, Erin Searcy. Raise your hand. Erin is the director of our strategic partnership activities, and so she's here. She's been here all week working with some of you all, talking about what Carnegie Mellon is doing and how our relationships can continue to grow. National labs are really focused on commercializing our tools and technologies where we can. So we have technologies and tools that could be used to address a variety of challenges, and we can further develop them together to translate that out into deployment into commercial industry. And then finally, research collaborations. The best partnerships begin with a conversation. We can talk all we want at the highest levels about wanting to collaborate, but it's really the ground roots. It's that grassroots effort to bring collaborations together, whether it's industry or academia. We look forward to partnering on problems. I know most of my colleagues here from the national labs will look forward to that. I'd say Jordan Henry, but he actually unfortunately had to leave. But Jordan and I have worked for decades together on a lot of problems in the national security space and in the energy space. And Jordan's from the National Lab of the Rockies. I'm from Pacific Northwest National Laboratory, and we are really excited to work with you and continue to grow the capabilities here. And with that, I will close, and I look forward to throwing out your sorry about that. We'll fix it. Thank you. So I'll say it for you, Daniel. Are there any questions? And we're going to preface it with saying, if you're a student, we really want your questions first.
You got it, Deb.
Thank you.
Any students in the room with the first question? Okay. Any questions from the audience?
Please.
Yes.
For some of your operations center research with the AI kind of like demo interface, how are you dealing with like SIP and CEII restrictions with AI training?
So maybe I better be careful first and tell you I'm not an energy person. So tell me what SIP and CEII are.
It's basically how are you able to incorporate the AI models with restricted data according to Nuremberg standards?
So when you say restricted data, do you mean nuclear data?
No, even just
So
access
proprietary.
information about where or how a substation is configured, things
Yeah,
like that.
yeah. Okay, so as I said, we do a lot of national security work. So we're very good at classifying data and being sure that we can protect data from whether it's a proprietary level, it's CUI, it's at a classification level. So we segment data within our systems to provide that. We work within a sandbox for our AI models, and so the sandbox does not learn from the data we're putting into that sandbox. We're just utilizing the data for that specific AI question. So that's one of the ways that we protect the data. If we want to learn from the data that we're actually building it with, then we sandbox all of that information. So we've developed many, many different models within the system to protect the data. One of the things that I didn't hit on here that we've been focused heavily on too is the assurance. So we build AI models for high consequence systems. And when you do that, you have to assure what the behaviors are going to be of that model, and you have to assure what the unintended consequences could be of that model. So we focus a lot on developing methods so that we can test the AI models in a variety of scenarios so that we understand how it's going to behave and how it's going to respond to different scenarios. So hopefully I answered your question without knowing what the acronyms were. Sorry about that. Anything else? Oh, Granger, no.
This is a softball question. Talk a little bit more about the battery test facility, which is working extensively with the private sector, right?
Yeah,
I mean, if I'm a battery developer, my understanding is I can bring it in and you guys can exercise it.
You can, thank you, Granger. And in fact, the Department of Energy, Office of Electricity put out a call, might have been 3 or 4 weeks ago, that provided an opportunity for anybody to submit a proposal to bring their battery research to the grid storage launch pad and be able to use our facility to test it. So our goal is that industry, this is a resource for industry. You know, we do the research, and a significant amount of research, but there's also a lot of other folks out there that are doing research on batteries and developing next generation batteries. But before you put them into practice, you have to test them. And not everybody has the facilities to do this testing, especially for large scale batteries. And so you bring your battery in, we set it up, we can use a variety of different capabilities to test it, a variety of parameters, putting heavy loads on it, reducing the loads immediately, temperature, different environmental conditions. And so I think the Grid Storage Launchpad is an amazing resource that is available to industry and academia for research to be able to test these systems out. So I encourage you, if you have a battery system and you want to be testing it, look up Grid Storage Launchpad. There's Department of Energy has a new call out to support that. Okay, thank you. It was a softball. It's in a contained facility. Yep, so if you didn't hear what Granger was just saying, he said you can blow the battery up, and it's in a contained space where it's okay for it to start a fire, and we have capabilities to handle all of that in that facility. Okay.
We have time for one final question, if there are any.
You got to give me time to fix your clicker over here.
Hi, I'm Kevin Hughes from PNNL. Just had one question about energy storage. a while back, I believe the only grid scale energy storage technology was pump storage, pumped hydro. sorry,
hydropower.
Pumped hydro. So today, do we know about roughly what percent of all the grid scale energy storage online right now is battery? Is it like 1%, 10%, 30%?
I apologize. I don't know the answer to that, but I'd be happy to talk to you afterwards and give an information for you.
Okay.
Yeah.
All right, thanks.
Yeah. Thanks.
All right.